A very good morning to all of you. Welcome to Science and Technology second class. And today we are going to start with nuclear energy. But before we do that, if audio and video are fine, please let me know. Wonderful. All right. So, what we are going to do today, first and foremost, we are going to start with this part of the energy module, which is nuclear energy. So first half will be about nuclear energy, and then after that, in the second part, we'll start with space technology as our second chapter. So this is what we are going to do, and I think towards the end of the day, we will be continuing with space technology as the chapter. Now, when it comes to nuclear energy, there are two parts into which nuclear energy is divided. And what I'm going to do is that first I am going to discuss with you the basics of nuclear energy, that is nuclear science, you can say in a manner. And the second part will be about nuclear technology. So first we'll discuss what is nuclear energy, what is nuclear force, and what is radioactivity, nuclear fission, nuclear fusion, etc. And then in the second part we'll have a discussion on nuclear technology, that is nuclear reactors, India's nuclear program, applications of nuclear technology, and all these things. So this is how we are going to discuss this part. Now first thing, this says nuclear energy. Now when we say nuclear energy, nuclear word comes from nucleus, meaning that this is an energy that is being derived from the nucleus, and that's why it is being called as nuclear energy. All right, so energy that we are deriving from the nucleus, and hence nuclear energy. This becomes energy from the nucleus of an atom, and that is why the term nuclear energy is being used. Now when it comes to nuclear energy, we need to understand how exactly is this energy coming from, where is it coming from, and what are some of the things that we need to know about nuclear energy. Before we do that, before we go into what nuclear energy is, let me also tell you briefly about how the atomic structure looks like, what the atomic structure is. So overall, when you look at the structure of an atom, what you would find is that there are electrons, protons, and neutrons. These are the three particles that you have in any given atom: electrons, protons, and neutrons. Now electrons, they keep on revolving, you can say they have their own orbits around a part called as nucleus. As you can see here, that all these electrons will have their own orbit, just like how planets have an orbit around the sun. Similarly, electrons also have an orbit around the central part, and this central part is called as the nucleus. The central part is called as the nucleus, and inside the nucleus we have two particles, one called as protons, which are positively charged, and then we have neutral particles, which are called as neutrons. So this is how the structure of atom is, that you have electrons on the outside, inside you have a nucleus is a very small space in which you have all the protons and neutrons packed together inside this nucleus. So this is what an atom looks like. Now when it comes to this understanding of electrons, protons, and neutrons, it's not that we have known about them forever. We discovered them, we understood that there are certain things that are there inside the nucleus, because when you go back to the original atomic theory, it used to say that atom is the smallest indestructible part of matter, meaning that atom is indestructible, there is nothing which is inside the atom. But then that theory was later dismantled when the discovery of electrons happened. And this is where a scientist by the name J. Thomson, he was the one who discovered electrons. He discovered electrons. And then, and his model of an atom was very different. He proposed a model which looked like, you can say, watermelon, where, I mean, if you cut the watermelon, what do you see? That there is a reddish colored part, and you have all the seeds embedded in it. So similarly, he also said that this is what uh, a given atom also looks like, that all the reddish part basically you can say is like a positively charged sphere, and all the seeds are negatively charged particles. So he did not say that there are positively charged particles, he just said that the entire region itself is positively charged, and only these small particles that you have in it, they are negatively charged, and these are electrons. So electrons this is where electrons discovery happened, you can say, in a manner. Now discovery of electrons happened, but he did not say that there were any protons, and this is where another scientist, Ernst Rutherford, he comes and discovers protons. So now he gave another theory, and he said that, look, majority part of an atom is empty, but there is a very small part inside the atom at the center of an atom, which is very highly concentrated and is positively charged. So there are positively charged particles that are there inside a very small portion in an atom. And this is a very small, I mean, let's say if you consider the size of an atom, suppose that if your room is of the size of an atom, then you just think of the nib of a pen, and that is what size of a nucleus could be. So just understand that nucleus size is very very small as compared to the size of an atom, and that's why he said that majority of an atom is empty, and there's a very small part inside the atom which actually contains all the positively charged particles. So in a manner you can say that this is how he discovered protons, and he was the one also to name those protons. But there was another scientist whose name should be mentioned, and this was Goldstein. Now, Goldstein also discovered, in a manner you can say, positively charged particles, but in a very different form. He did not talk about the atom or what's present inside the atom or the nucleus, but rather what he said is, he was doing his experiments, and there was a cathode ray tube experiment where he found that there are positively charged particles. So he did say that there are positively charged particles that exist, but he did not say it as a part of the atom or as a part of the nucleus. He just said that there are positively charged particles, and this was almost, you can say, 20 years before what Rutherford had done. So Rutherford uh, discovered protons, I think, in 1915, 1917, I think, and Goldstein had done his experiment in 1893. So almost 20 years before what uh, Rutherford had done. Yet, normally we say that Rutherford was the one to discover protons because he was the one who properly defined it as a part of the nucleus and the particles that are there. Now, after this, until now, positive and negative charges were all discovered, but this is where neutrons were still not discovered. And then discovery of neutrons happens, and this is done by James Chadwick. So James Chadwick, he discovered neutrons. He discovered neutrons. So he was the one to define the neutrons and that the neutrons are present. Now, how we came to know about neutrons is also important and interesting. That it was based on the concept of isotopes. Anyone who can tell me, anyone who remembers what isotopes are? What are isotopes? Anyone quickly? Hmm. Yeah, Tarun, you are correct. Jia, you are correct. Kola, you are correct. Pooja, you are correct. Himanshu, you are correct. Hmm. Some of you have just written the opposite of what it is. Yeah. So this is what isotopes are. Isotopes is where you have the same atomic number but different mass number. Same atomic number but different mass number. Now what do we mean by atomic number and what do we mean by mass number? So can you tell me this? What is the meaning of atomic number? What is atomic number? Number of protons. Perfect. Some of you have written number of electrons, but while defining atomic number, we never define it as number of electrons. We define it as number of protons. So atomic number will be defined as number of protons. And I'll tell you why. The reason is that getting rid of an electron or adding an extra electron in any given atomic configuration is not that difficult. You have many charged particles, correct? Positively charged particles and negatively charged particles. Now, when you have negatively charged particles, it means that there is an extra electron in the atomic configuration, and that's why it is a negatively charged particle. And at the same time, when you have a positively charged particle does not mean that it has an extra proton. Positively charged particle means that it has a less neutron. All right. If it has one less neutron, sorry, electron, electron. If it has one less electron, then in that case you will say that it is positively charged. So that's why number of electrons can change, but number of protons cannot change that easily. Number of protons becomes the most intrinsic property of any given element. So that's why when we define any element, we define it on the basis of the number of protons. Hence, number of protons is the most important property of any given element. Now, that's why atomic number is always defined as number of protons. Now, can you tell me what is mass number? What is mass number? Yes, Himanshu, Saimeen, Dikshit, Pooja, everyone, you have given correct answer. Mass number basically means number of protons plus neutrons. So this is called as mass number. So atomic number and mass number. In case of isotopes, we are saying that the atomic number is same, mass number is different. Now atomic number same also means that you are talking about the same element. If the atomic number changes, the element is different. So for example, the atomic number 1 belongs to hydrogen, 2 belongs to helium, then 6 belongs to carbon, 8 belongs to oxygen, 7 belongs to nitrogen, and so on. So that's why atomic number or the number of protons becomes the most important property in defining any element. And then mass number is something that can also be variable at times, and that is what we'll discuss later. So overall, this is what it is, that we are talking about same atomic number and different mass number. Now, as the scientists were working on understanding of different elements and different atoms, this is where these concepts started to develop. Now when it comes to these concepts, what happens here is that overall in the case of this concept, initially when we looked at all the isotopes, we saw that the nucleus of the isotope, they have the ratio of their masses in the ratio of 1 is to 2 is to 3. In case of hydrogen, 1 is to 2 is to 3. Now it was well known that hydrogen has one proton and one electron. So if there is only one proton and one electron, then why is the mass in the ratio of 1 is to 2 is to 3 whole number ratios? Because if let's say the masses were changing because of electrons are very lightweight as compared to protons. Almost, I mean, protons are almost 2000 times heavier than an electron. So that's why if let's say the masses were happening because of electrons, there should have been 2000 extra electrons, which is not the case. So that's why there is something that is adding to the mass, and this is where uh, the concept started to develop, that there must be something else apart from the proton inside a nucleus which has mass but does not carry any charge. because protons carry positive charges, electrons carry negative charges. This is a neutral atom, does not have any charge, neither positive nor negative. So it means that there must be something which has mass but doesn't have any charge, and that's why the name neutron was given to such a particle, where the neutron has mass but does not carry charge. And why it was in the ratio of 1 is to 2 is to 3 is mainly because mass of protons and mass of neutrons are almost equal, almost equal. So that's why we saw that whole number ratio of 1 is to 2 is to 3. So this is how 1 is to 2 is to 3 is coming, that if you look at hydrogen with mass number 1, mass number means hydrogen 1 means what? Number of protons is 1, and mass number is 1 also means that number of neutrons is how much? How many neutrons? 0. Perfect. That's why mass number 1, because mass number is what? P plus n. So if P is already 1, then n has to be 0. Then the second isotope that we have is deuterium. So deuterium means what? Again, proton will be 1 and neutron will also be 1. Then only the mass number becomes 2. And in hydrogen 3, proton will be 1 and number of neutrons will be 2. Then the mass number becomes 3. So these are the three isotopes of hydrogen, all of which have one proton each, and the neutrons, number of neutrons is 0, 1, and 2. So this is where the understanding of the neutron happened, that this is how a neutron should be, this is what a neutron should be inside the nucleus. Now, as the number of neutrons etc were also discovered, this is where we come to the next stage in the understanding of a nucleus or an atom, where we are talking about mass and energy of a nucleus. Now in this context, what we see is that initially uh, we did not understand the relation that could be there between energy and mass. We used to see energy and mass as completely two different entities, and not knowing that there could be a relation between mass and energy. And this is where there was something that was happening which the scientists could not understand well. This is the concept of mass defect. Now what they found is that if, let's say, you have one proton and one neutron, suppose the weight of one proton is 10 grams and weight of one neutron also is 10 grams. So if, let's say, there is any nucleus inside which you have one proton and one neutron, then the weight should be how much? Weight should be 20 grams, right? Weight of the nucleus should be 20 grams. But what they found is that the weight of the nucleus is not 20 grams, but rather it is lesser than that. All right, it is lesser than that. So for example, let's say it is 15 grams or 16. These are not original figures, these are just, I mean, I'm just giving you an example. So they found that it's not 20 but it is 15. Now they were perplexed, because if, let's say, it was more than 20, then it could have been explained that fine, there must be something else that we don't know of, and hence, let's say, if it was 24 or 25 and so on, then there must be something else which is adding to that extra mass. But if the mass is lesser than the individual masses of protons and neutrons, then how is it happening? They could not understand, and that's why they named it as mass defect. So that's why nuclear mass is found to be always less than this, less than the mass of proton plus neutron, and that's why this difference in mass is called as mass defect. So now, until now, they understood that they did not have a good understanding of why it was happening. So that's why they called it as mass defect. And then comes a scientist whose name will keep taking in every chapter, and that is Albert Einstein. And Albert Einstein, through his theory of special relativity, gave an equation. E is equal to mc squared. And I'm sure that many of you have heard of this equation. I'm not saying whether you know the meaning of this equation or not, but I'm sure that somewhere here and there you might have heard this E is equal to mc squared. Now, this E is equal to mc squared now became very crucial, because this is what defined the relation between energy and mass, because E here is energy. E is energy, M is the mass, and do you know what is C? Yeah, speed of light. Perfect. C is the speed of light. C is the speed of light. So now this is what was defined, that there is a direct relation between energy and mass inside the nucleus. And when they did this calculation, that when the mass was being lost, the loss of mass was equivalent to amount of energy that was being released out of a given nucleus. So now this was explained, that this was not mass defect, but rather mass changing into energy. All right. This was now defined, that this was happening happens because mass changes to or releases energy. It converts to instead of changes. Right. So mass converts to or releases energy. So this is now something that was understood, that okay, fine, this is what's happening, that mass is actually converting to energy, and it's not that mass is being lost or something is happening that we are not able to understand at all. Now what they found here is that this energy that is associated with mass is enormous amount of energy. Just imagine this. Just look at this basic equation, that if let's say mass is equal to 1 kg, suppose the mass of a bunch of nuclei is 1 kg, then how much is the energy? Energy is 1 into 3 into 10 to the power of 8 squared, which is 9 into 10 to the power of 16 joules of energy. So 1 kg of mass is equivalent to 9 into 10 to the power of 16 joules of energy, if we go by this logic. So overall, this is where we saw that this was uh, an extreme amount of energy that we can derive out of the nucleus. And this is where we started to understand that this could be a source of energy that we can use to even generate electricity, that it can maybe solve our energy problems. And if we, because we were looking at the alternatives, we had started looking for the alternatives, and this looked to be a very good alternative to the energy that we have, to the energy sources that we have. And this is where they started working on it. But unfortunately, before doing anything else, they made an atom bomb and they dropped it on Japan. And after making the atom bomb and after making all the nuclear weapons of the world, and this is where they started working on electricity also. But until then, there was no electricity that they were working on. So unfortunately, this enormous amount of energy that they found, first it was used for wrong reasons before coming to the right reasons it should be used for. So overall, this is basically what we see, that now they had a basic understanding of that. Now the fact that energy and mass, they are interconvertible, and mass, when it comes to energy inside the nucleus, there is an equivalent amount of energy that is associated with mass that is inside the nucleus of an atom. And hence this is where they understood that this could be an enormous source of energy for us altogether. Now when it comes to the understanding of this energy, one thing that becomes very crucial also to understand is that there is a concept called as nuclear binding energy. Now nuclear binding energy is nothing but the energy with which the nucleus binds the protons and neutrons. So nuclear binding energy is the energy with which a nucleus binds protons and neutrons, protons and neutrons inside it. So this is what we define nuclear binding energy as, and this is where the concept of nuclear force also comes here, that force associated with the nuclear binding energy is called as strong nuclear force. Strong nuclear force. So this is, now understand this, that we are talking about two concepts, one called as nuclear binding energy, another one called as strong nuclear force. Now nuclear binding energy, what we are saying is that this is the energy with which the nucleus binds all the protons and neutrons together. Now understand this, that this energy has to be enormous amount of energy. And why so? Protons, you might know about this, and I'm sure that you have heard it somewhere in the early classes, or maybe class 6th, 7th, 8th, etc. We say that like charges repel each other, unlike charges attract each other. Have you heard of it? Do you remember this? I'm sure you've heard of it, right? We say that like charges repel each other and unlike charges attract each other. Meaning what? That when you have two like charges, meaning positive charge and positive charge in case of protons, then they would repel each other. And when you have unlike charges, meaning a proton and an electron, then they would attract each other. Similarly, in magnetism also, you might have come across this, that you have north pole and north pole, they would repel. If you have north pole and south pole, it will attract. So similarly here also, when you have two protons, they will repel. When you have electrons and protons, they would attract. Now inside the nucleus you have only protons, right? Protons and neutrons. So obviously they are repelling each other all the time. There is a lot of force of repulsion inside, and nuclear binding energy has to be strong enough that it is still able to contain all the things together. And that's why the force that is associated with this nuclear binding energy is called as the strong nuclear force. And strong nuclear force is the strongest fundamental force in nature. There is no other force which is stronger than strong nuclear force. There are certain other forces also, and we'll discuss that later. But strong nuclear force is the strongest of all the forces that we know of to naturally occur. So this is basically where we find the understanding of a basic understanding of nuclear binding energy and strong nuclear force. Now, when it comes to these concepts, we understood that fine, the nucleus is packing a lot of energy, and then we realize that there are different ways in which we can get hold of this energy. There are ways in which this energy is released out of the nucleus. One is a natural way, which is called as radioactivity. Then there is another natural way, which is called as nuclear fusion, which is seen inside the sun. And then there is another way in which a nucleus might break and release a lot of energy, and that is nuclear fission. So radioactivity, nuclear fission, and nuclear fusion are three ways in which we can get hold of this energy packed inside the nucleus. The first one here is called as radioactivity. But before we go to radioactivity, whatever we have discussed until now, any doubts in it, anything that you want to ask, any question if you have for me? 1:2:3, please tell once again. So 1:2:3 basically is the ratio of masses of hydrogen nuclei. So that is where the discovery happened from, that we know that there is only one proton in each one of them. So how is it possible that the nuclear weight is in the ratio of 1:2:3? So that's where there must be something else inside the nucleus apart from the proton that is adding to this mass, and this is what was called as neutron. because it does not carry any charge but carries mass. Mass defect, once again, in case of mass defect, what we are saying is that suppose that you have any nucleus, and inside the nucleus there is one proton and one neutron. Suppose 10 grams each is the weight of them. So nuclear weight, or the weight of the nucleus, should be 20 grams, but it is actually seen that it is not 20 grams but less than that, maybe 15, 16, 14 grams only. So that difference that is there between the actual mass and the mass that should have been, that difference is called as the mass defect. And this mass defect happens because there is some energy that is released when the all these things are being bound together, and that is basically because of the energy, that is nuclear energy. So that mass lost is in terms of the mass lost is in terms of that nuclear energy. Mass is converting into energy. Mass in E is equal to mc squared is the mass of the nucleus, not really nucleus, but rather the subatomic particles. The masses of the subatomic particles and the energy that these subatomic particles together have inside the nucleus. What are proton, neutron, and electron? Protons are positively charged particles, neutrons are neutrally charged neutral particles, and electrons are negatively charged particles. All of them are found inside an atom. Why a strong nuclear force is required? It's not about requirement, it's naturally there. Because if there is no strong nuclear force, it will not be able to bind all the nuclear particles like protons, neutrons, etc. together. And that's why you need a very strong force for that. And that strong force is called as strong nuclear force. Explain the difference between nuclear binding energy and strong nuclear force. There's no difference between them. The strong nuclear force is a force, and energy associated with this force is called as nuclear binding energy. Why nuclear fusion is not possible yet? Nuclear fusion is possible, it happens inside the sun. You are saying that artificially we haven't been able to succeed in it. uh, we'll discuss that when we go to nuclear fusion. We'll discuss that there. Not able to understand a few topics. You go through the lectures again. I mean, if required, go through the recordings again. If you have any questions, ask me. I'll ensure to help you with it. Nuclear force is to hold together protons and neutrons. Since neutrons have no charge, why would it be the strongest force? Shouldn't the strongest force be the one holding protons and electrons together? Not really, because see, neutrons not having charge does not mean that it is not having the force, or let's say even uh, the other aspects of force in it, because force does not always associate only with charges. Here we know that electrostatic charges in protons are adding to that extra force, but neutrons by themselves without having any charge also, they carry force. They carry a force which is because of their uh, configuration, but that's where weak force and bosons etc come from. We don't need to go there uh, into that segment. It's a very complex segment, but just remember this, that it's not that only charges will exert force. Even without having charges, forces can be exerted. Let's say gravitational force as an example. It's not related to any kind of charge, but yet it's a force that exists. So similarly, neutrons also carry force. Does atom come from subatomic particles? No, subatomic particles together will make up the atom. How mass converts into energy with example. This is the example that when the protons and neutrons are inside any given nucleus, this is where you have that energy that exists, and hence this is where mass, while if let's say if these two are coming together, or even if you're releasing some of these particles, they would release a lot of energy. So mass converts into energy in that sense. Is equal to mc squared applicable for nuclear fusion as well? There the things are a bit different. We'll discuss that later. Why is there repulsion in nucleus? It's because of protons, because of the presence of protons. Are protons, neutrons, electrons visible to eyes? No, not at all. Nucleus is different and consists of protons and neutrons. Yes, that's correct. Is nuclear force binding the earth? No, it's a very different story altogether. Sorry for asking such a basic question. No, you can ask whatever questions you have. I mean, as long as it makes it clear for you, you can ask any question that you want. Quarks, hadrons, etc. We'll discuss about quarks, hadrons later. It's not related to what we are discussing currently. Nucleus has a positive charge. Yes, you can say that because of the presence of protons. All right. So let's move ahead. So now what we know is that this nuclear energy that we are getting, there are three ways in which we can get this nuclear energy. There are three sources or three different mechanisms of getting this energy. The first mechanism is radioactivity. Now, in case of radioactivity, what we are saying is that an unstable nucleus undergoes a decay, which is called as radioactive decay. Now, when we say unstable nucleus, what is the meaning of an unstable nucleus? There are two ways in which we define a nucleus to be unstable. First is when the number of protons is very high. So this is one way in which instability comes in. And second is when number of protons is not equal to number of neutrons. So then in that case also we say that it is unstable. So there are these two ways in which instability might come in. All right, there are these two ways in which instability might come in when it comes to any nuclear material. Now in this particular scenario, when it comes to radioactivity, there are three ways in which this decay happens. One called as alpha decay, one called as beta decay, and another one called as gamma decay. So we also denote it like this: alpha decay, beta decay, and gamma decay. All right, alpha, beta, gamma. Now, when the number of protons is very high, the kind of radioactive decay that happens is called as alpha decay. When the number of protons and number of neutrons are not equal, the kind of decay that happens is called as beta decay. And normally what we see is that gamma decay happens whenever alpha or beta decay has happened. So we'll discuss about that later. So first kind of decay is called as alpha decay, and it happens when the number of protons is very high. So it takes place when number of protons is very high. And this normally takes place in heavy nucleus. So it takes place in heavy nuclei. Now just understand this. What exactly are we saying? In case of alpha decay, we are saying that the number of protons is very high. Now what happens when the number of protons is very high? Obviously they have positive charges. Obviously they are exerting a force, and as the number of these protons would increase inside any given nucleus, obviously the amount of force that they are exerting on the nucleus will also start becoming very high. Now, one thing about the nucleus is that the size of nucleus does not increase in the same ratio as the number of protons does. Meaning that, let's say, and it basically increases as a cube root of number of protons. Meaning when you have one proton, the size of nucleus is, if it is 1, then when you have 8 protons, then the size becomes 2. When you have 27 protons, then the size becomes 3. When you have 64 protons, then the size becomes 4, and so on. So that's why the size is not increasing in the same ratio as the number of protons increasing inside the nucleus. So this is what will cause a lot of instability after a while. Just imagine that we are in an online class, but suppose if we were in an offline class. Now in an offline class, what happens? There is a seating arrangement. Let's say it has a strength of seating strength of 100 students. Suppose you all come and you sit in the classroom, and less than 100 students are sitting in the class. So then seating arrangement can be managed easily. But then let's say I also ask the morning batch students also to come and sit here, and then 100 more students come and sit. Now there is no space. The class capacity is only 100. So what happens next? A lot of instability. A lot of instability. You will start fighting, and you will maybe throw out all those students, because you would say that you are the original owners of this class. They are not. So this kind of instability happens, and people will be thrown out of the classroom. Now something similar happens inside the nucleus as well. That inside the nucleus, as the number of protons and neutrons starts to increase, there is a number after which it becomes impossible for the nucleus to sustain all the protons and neutrons inside it. And this is where we see that alpha decay takes place. So alpha decay, that's why, will happen only in the heavy nuclei, where the number of protons is very high, the nucleus becomes very bulky, and a lot of force is being exerted by the protons to the nucleus, and this is where it becomes very bulky, and ultimately you might lose some of these particles. So this is what exactly happens in case of alpha decay, that the number of product nucleus is less than that of the decaying nucleus, while the atomic number is decreased by 2. If you look at this picture, you can see this, that the atomic number has decreased by 2, and the mass number has decreased by 4. So that's why alpha particle is said to be equivalent to the helium nucleus. So helium nucleus meaning how many protons and how many neutrons? How many protons and how many neutrons? Yes, 2 each. Correct. 2 protons and 2 neutrons. That's why the mass number is 4, 2 plus 2. I know. So number of protons being 2 and number of neutrons also being 2. So meaning what? That 2 protons and 2 neutrons are lost from this heavy nucleus. So from this heavy nucleus, 2 and 2 of both will come out. This is what happens in case of alpha decay. Then after that we have beta decay. Now in case of beta decay, what we see is that this would happen when the number of protons and number of neutrons is not equal. Number of protons and number of neutrons is not equal, and it can take place in heavy and light nuclei. So it can happen in any nuclei. Whenever you have number of protons and neutrons not being equal, there you will see that this can take place. This is something which is possible there. Now, if you look at these two examples that we have right here on the board, just understand this, that first we are taking carbon 14. Now carbon 14 has 6 protons and 8 neutrons. That's why 14. So carbon 14 has 6 protons and 8 neutrons. Now this converts into nitrogen 14. So this nitrogen 14 has 7 protons and 7 neutrons. So this number which was 14 remains 14. There is no change in the mass number. All right, there is no change in the mass number. So that's why just remember that in beta decay, mass number remains unchanged. So this is what happens. So there will be a conversion where we see that there is one proton extra and one neutron less. Now, one proton extra and one neutron less. Basically, what happens is that the configuration inside the nucleus itself changes, and a neutron changes to proton. Neutron converts to proton. So it's not that a proton is coming from outside somewhere. It's just that internally the configuration is changing and a neutron converts to a proton. And in the second case, if you see, you have carbon 10. Now, in case of carbon 10, again, you have 6 protons and 4 neutrons, and it changes to boron 10. And this boron 10 has 5 protons and 5 neutrons, and that's why it becomes stable, because the number of protons and neutrons being equal means stability. So here what we have seen is that there is a decrease of one proton and there is an increase of one neutron. So that's why in this case what we are seeing is that a proton converts to a neutron. So again, internally the configuration changes, and this is what happens to attain stability. It's all about attaining that stability. By releasing those particles also, they would partially become stable. Similarly, by changing this configuration internally also, they would become a bit more stable by having the same number of protons and neutrons. So this is what happens in case of alpha decay and beta decay. Now in case of gamma decay, what we observe is that the nucleus in an excited state spontaneously decays into ground state, and a photon is emitted with energy that is equal to the difference in the energy levels of these two energy levels of the nuclei. Now, when it comes to gamma decay, we are saying excited state. The meaning of excited state is when you have more energy than usual. Excited state means more energy than usual. More energy than usual. And the meaning of the term ground state is that this is the normal energy level. This is the normal energy level. So this is how we define gamma decay. That in case of gamma decay, we are saying that the nucleus right now has extra amount of energy. It is in an excited state, and we have to get rid of that extra energy so that it comes back to its ground state or relaxed state. And this will often happen whenever alpha or beta decay happens. So gamma ray is emitted when alpha or beta decay results in daughter nuclei in an excited state. So after alpha decay or beta decay, gamma decay takes place as a result of alpha and beta. So this is how we see that alpha, beta, and gamma decays, they take place. So in case of gamma decay, this is what we precisely see, that there is an excited nucleus which comes back to the relaxed state or the ground state by releasing some extra energy in the form of gamma rays or gamma particles or gamma photons. You can say anything. So just remember that this is what's happening. Now, all the explanation aside, you just need to understand all these things only in one single sentence each. Alpha decay happening when you have a bulky nucleus, so it will release some particles to become stable. Beta decay happens when proton and neutron numbers are not equal, so they would change the configuration in a manner that the number becomes equal, and hence they become stable. Gamma decay happens when you have extra energy. They would lose that extra energy to become stable. So in one line each, just remember this, in one line each. All the other explanations and all the details that we've gone through, that is probably not required for your examination. Only one line each from these three is enough for you. One is alpha, when you have heavy nucleus. heavy nucleus releases some particles, becomes stable. Beta decay, when the number of protons and neutrons is not equal, that number becomes equal, they become stable. Gamma decay, when there is extra energy, they lose that extra energy, they become stable. So just remember this one line each about alpha, beta, and gamma decay, and you don't need to know anything else apart from these three lines. All the explanations that I've given, you can say that's just extra information in case you need to know. Otherwise, I don't believe that that can come in the examination. If at all, only these three lines can come in the paper. All right. So this is what happens in case of radioactivity. Now, after radioactivity, the second way in which we get this energy inside from inside the nucleus is called as nuclear fission. Now, can you tell me the meaning of the word fission? What is the English meaning, the dictionary meaning of the word fission? Yeah, to split, to divide, to break. Correct. So, fission means what? Fission means in a manner to split or divide or to break. Right. So nuclear fission, that's the meaning, that this is where the nucleus is breaking. The nucleus breaks, and while the nucleus breaks, it releases a lot of energy. When it breaks, it loses a lot of energy, it releases a lot of energy, and that becomes the source for us to get that energy and convert it into electricity. So that is what nuclear fission is. Now in case of nuclear fission, what happens is, if you look at this particular picture, this is how nuclear fission works, that we have this nucleus of uranium 235. Now about uranium, just remember that uranium has various isotopes: uranium 233, uranium 235, uranium 236, uranium 238, uranium 239. There are so many different isotopes of uranium, out of which uranium 235 and uranium 238, these are natural. These are natural isotopes. The others basically will be formed in one reaction or the other. One some kind of nuclear reaction, etc., will create the other uh, isotopes, but uranium 235 and uranium 238 are the natural isotopes, out of which uranium 235 is the one which is fissile. Uranium 235 is fissile. Fissile meaning that it can undergo fission. All right, it can undergo fission, so that's why it is called as being fissile. So uranium 235 is the only naturally fissile element. All right, uranium 235 is the only naturally fissile element, meaning the only natural material that has the capacity to undergo fission. So others you cannot make it undergo fission directly. You will have to use another procedure to do that. So now what we do is that that's why we will be using uranium 235 to cause fission. So now in this uranium 235, we bombard this uranium 235 with a neutron. All right, we bombard this uranium 235 with a neutron. So now it obviously becomes uranium 236. Now this uranium 236 is highly unstable. Uranium 236 is highly unstable, and it just breaks. Uranium 235 would not break. Radioactivity will happen in it because it's bulky, it's heavy. So radioactivity would happen in it. But when you bombard it with an extra neutron, it becomes uranium 236, and this uranium 236 is very unstable, and it just breaks into two parts. And while it breaks into two parts, it releases a lot of energy. It releases a lot of energy in the form of kinetic energy and gamma rays. So a lot of energy will be released here, and apart from that, it has broken into two parts: krypton and barium. Krypton and barium. So doing that, apart from that, there are three extra neutrons also that have been released here. Now just see this simple mathematics. You have 236 on this end, you have 92 plus 141 on the other side. 236 here, 92 and 141 on the other side. So which is equal to how much? 233. 92 plus 141 is 233. So there are three extra neutrons left. So this is what we are accounting for, that there are three extra neutrons which are left after this reaction. Now these three extra neutrons will not stop here. They will now start causing further fission, that from here on another fission will be caused. So three extra neutrons will be produced from all these three extra neutrons. So similarly, from this also again three extra neutrons will be produced like this. Like this, and this will continue. All right, this will continue, and it basically sets up a chain reaction. So that's why just remember that it's not that the reaction would happen only once. The reaction will keep happening, and that's why it releases an enormous amount of energy. It can release a huge amount of energy because of this. And it's not that, because when the reaction is happening, it's not that you have just one nucleus or you have just one atom. Even if you have 1 gram of uranium, let's say you have just 1 gram of uranium, do you know how many particles of, or how many nuclei can be there inside just 1 gram of uranium? Do you remember there is something called as Avogadro number? Class 10th chemistry, you might have come across it. And then again, for those of you who took science, maybe again back in class 11th, there is something called as Avogadro number, if you remember. So that Avogadro number is how much? Anyone who remembers the value of Avogadro number? Yeah, billions of neutrons will be produced. That's correct. Yeah, 6.022 into 10 to the power of 23. So, meaning that when it comes to even 1 gram of uranium, if you do those calculations, you'll find that there are 10 to the power of 21 particles of uranium in just 1 gram of uranium. So just imagine the amount of reaction that can happen, the number of steps that will be set up here. So that's why this will just lead to a chain reaction. Now this chain reaction will obviously produce a lot of energy. Now there are two things about this chain reaction. First thing is to control this chain reaction, because if we control the chain reaction, we get electricity. If you don't control the chain reaction, you get atom bomb. So the things can be that simple, that you control the energy, you get electricity. You don't control the energy, you get atom bomb. So what happens here is that there is a chain reaction setup. There's a chain reaction setup. Now this chain reaction, if controlled, if the chain reaction is controlled, then you get electricity. If this chain reaction goes uncontrolled, leads to the creation of atom bomb. So that's why we need to control this chain reaction, correct? Now to control this chain reaction, we need something which is called as critical mass. To control the chain reaction, we need critical mass. Critical mass is that mass of nuclei of a nucleus when a controlled chain reaction could be set up. So that's why smallest amount of fissile material needed for each fission reaction to produce at least one more fission reaction on an average. So what, in simple terms, what we can say is that this critical mass is mass of nucleus required for controlled chain reaction. Controlled chain reaction. So that's why critical mass becomes essentially important, because if you are below critical mass, the reaction quickly stops. If you are above critical mass, the reaction can go uncontrolled. So that's why you have to just maintain that critical mass. You have to determine the critical mass and you have to maintain that critical mass. Neither you can go above it, because that will create an atom bomb, nor you can go below it, because then it will make the reaction just stop over the next few seconds or a minute. So that is basically what comes in when it comes to critical mass. And critical mass every now and then will be uh, in the newspapers also. They would say that a reactor has reached criticality. When they say that a reactor has reached criticality, it means that now it has attained critical mass, and hence the operation of this nuclear reactor can be started. Very recently also it was in the news that a reactor, an Indian reactor, has now reached criticality. So if it has reached criticality, it means that now you can start with the reaction, you can start with the operations of the nuclear reactor. So that's why critical mass becomes a very very important term in terms of making sure that the reaction can sustain, or you can keep going on with that reaction without causing any harm. So that's why this term becomes very crucial in ensuring that critical mass is reached, and hence the reaction can safely go uncontrolled. So last year, sorry, not last year, last month, it was in the news that the Kakrapar 4 reactor that we have, the Kakrapar 4 critical, the reactor that we have, which is almost a 700 megawatt reactor. This basically has uh, reached criticality. This is the one, if you remember, you might have read maybe that it is in Gujarat. So this reactor for India, it reached criticality, meaning that now we can start with the operations of the nuclear reactor. So in this manner we see that this is how critical mass becomes critical, becomes very important for attaining a sustained controlled chain reaction. Then another problem is with regards to uranium 235, the availability of uranium 235. One thing we understand, that maintain critical mass so that reaction can become controlled and you can generate electricity from it. Now the other problem is that when we do the mining of uranium, natural uranium has two isotopes. We discussed this. You have uranium 235 and uranium 238. Correct? These are the two isotopes of uranium, natural isotopes of uranium. Now if we have done uranium mining, if we have, let's say, 100 grams of uranium, out of these 100 grams of uranium, 99.3 grams is just uranium 238, and only 0.7 gram, only 0.7 gram is uranium 235. Now this is basically how we look at uranium. All right, so uranium 235 and uranium 238. So 0.7 gram of uranium 235 and 99.3 gram of uranium 238. Now uranium 238 is not usable for us. It's uranium 235 which can cause fission. Uranium 238 does not cause fission. Even if you bombard it with an extra neutron, nothing happens. All right, it will just simply digest it. Radioactivity will keep on happening in it, but it will not break. So uranium 238 doesn't break. Only uranium 235, when bombarded with an extra neutron, it breaks. So now this is a problem, because the one that is usable is available as just 0.7%, and the one which is not useful is 99.3. So then in that case what we do is that we convert a part of uranium 238 to uranium 235. and this process is called as enrichment. This process is called as enrichment. All right, this process is called as enrichment. So enrichment basically is the process where we increase the concentration, of uranium 235. All right, so from 0.7% it goes on to almost 3 to 5%. From 0.7% to 3 to 5%. This process is called as enrichment. So overall, that's why the process of enrichment becomes very crucial, because then you will be able to increase the concentration of uranium 235, and hence will be able to get some extra energy out of the same. Otherwise, it becomes very difficult for us to get the required energy only from 0.7% of this concentration. Now, one thing that you have to understand here is that it's, you may ask that why are we then doing it only to 3 to 5%? Let's convert 100% of this uranium 238 into uranium 235, because then we'll have extra amount of uranium 235, and then we can do a lot of, we can get a lot more of energy from it. Why not do that? And then there is a reason for that. As you go beyond 5%, this is when it starts becoming very reactive and very unstable, and then you can create an atom bomb out of it. So up to 5% electricity, above 5% nuclear bomb. All right, up to 5% enrichment means electricity, above 5% means atom bomb. So this is what happens. So that's why the enrichment levels do not have to go beyond 5%. And this is where you'll see that internationally also a lot of monitoring will be done. Recently, for example, it has been in the news last year, for example, when US said that Iran now has reached 85% enrichment. And it was a controversial news last year that Iran now has reached 85% enrichment. So 85% enrichment means that Iran is creating atom bomb. There is no electricity that you produce beyond 5%, because it becomes very unstable to be used in nuclear reactors. So that's why beyond 5% you can't. And beyond 5%, anyone, any country that is doing an enrichment beyond 5% means that they are creating an atom bomb, and they're not really using it for electricity production. So that's why once in a while this term enrichment also will be in the news, where some country or the other will talk about their enrichment and how much enrichment they are doing, and how they are trying to limit the amount of enrichment and so on. So that's why just remember that these are some of the things which we have to take care of, especially in case of nuclear fission. Any question? Any question with regards to whatever we have discussed? Is there any use of uranium 238 without enriching it? Normally only to get radiations out of it we use it. Otherwise uranium 238 does not really have a use for us. The radiations from it that we get is what we can use. Why uranium 238 is less? It's just the natural configuration of the element. We cannot control it. It just naturally occurs like that. All isotopes undergo beta decay, apart from the one where you have equal number of protons and neutrons. The all the others can undergo beta decay, apart from hydrogen. Hydrogen cannot undergo beta decay. Apart from that, any other isotope where you have unequal number of protons and neutrons, you would see decay happening there. Nuclear fission uranium diagram, please. This is the diagram. How to enrich 238 to 235. Basically, just like if you know about centrifugation, how centrifugation is done. Suppose okay, milk into curd, sorry, milk into fat. How we get fat from milk, do you know that? That we use a centrifuge where milk will be rotating very fast because of centrifugal force, and then because of the difference in their densities, we'll see that fat is something that comes out of the milk. So very similar manner, a centrifuge is used in separating out uranium 235 and uranium 238. Does India have does India have uranium sites? I mean, if you are asking about whether we have reserves, we do have reserves. There are mines in Jharkhand, there are mines in Andhra Pradesh. All these areas, they do have it. If enrichment above 5% is harmful, so why America and Russia have so much of atom bomb? Uh, the simple answer here is hypocrisy. That they did it first, and after that they started preaching the world that please you don't do it. We have done it. We have created all the atom bombs that we could. Now I don't want you to do it. Please explain this diagram. Okay, so what I'm saying is, just once more, what I'm saying here is that we take uranium 235, we bombard it with a neutron. So this neutron goes and sticks to this uranium 235, and hence it becomes 236. That's why atomic number remains unchanged, mass number changes because you have one extra neutron. Now this is very unstable, and because of that it breaks into two parts of krypton and barium. Now, krypton plus barium, the mass number is, if you see, 92 and 141, total of 233. So there are three extra neutrons left. So these three extra neutrons will further go on bombarding all the other neutrons that you, sorry, all the other nuclei of uranium 235, and it sets up a chain reaction from here, releasing a lot of energy. Is there any isotope where the number of protons is equal to the number of neutrons? Yes, every element will have one isotope which has equal number of protons and neutrons. For example, carbon 12, oxygen 16, nitrogen 14. All these are examples of where you have extra, I mean, equal number of protons and neutrons. So always there will be one isotope which has equal numbers, and then there will be other isotopes which have unequal numbers. Why only uranium 235 undergoes fission? The answer to this is in terms of weak nuclear force, but goes beyond what we are discussing here. Do we need to know about India's nuclear power stations? Not in terms of data, but some of the things that we need to know. We'll discuss that later today. Is there any end to the chain reaction? Yes, there is. There will be a time when the number of neutrons is not enough for causing another step. So this is where it will end. Only neutrons is realized and further neutrons hit another nucleus. Yes, it's only about neutrons. How much energy does 1 gram of uranium create? It creates almost 10 to the power of 12 joules of energy. How uranium 233, 36, 39 will be produced? We'll discuss that. You will see some of the examples where you'll see that how others are also produced. Why not other isotopes? I'm not sure what your question is. Can you repeat it? Can thorium be used for energy production? It can be used, and we'll discuss about that later. Using variable devices causing absorption of radioactive material more than standard amount recently in newspaper last year. Uh, if you could share the link with me in the email, I'll be better able to understand what your query is related to. To what extent should we know about other countries' uranium production and all? We don't need to know about it unless it is in the news for some reason or some kind of controversy it has been in. Otherwise, we don't need to. Why we not use uranium for other than mass 235? Because as I said, that others are not capable of fission. They do not undergo fission at all. Their configuration is different. In Chernobyl, after nuclear disaster, can we go to the place without protection? We can't, because there are long-lived radioactive wastes which have been produced, and the radiation amounts are still high. If we eject electrons by photons, will it produce electricity? Very good question, but it would not do that, because electrons are very easily ejected, and that's why the amount of electricity that they'll produce will be pretty less. How nuclear accidents happen? We'll discuss this. Difference between fission and fusion. We haven't discussed about fusion, so just wait. Is neutron split into smaller neutrons in the blue arrow in the image? No, the blue arrows basically mean that from this one neutron, three more neutrons are being produced. From that, three more extra neutrons are produced, and this is what we are saying, not splitting. Neutrons won't split. Hmm. Right? So, this is about nuclear fission. Now, before going to nuclear fusion, let us take a small break. Let's take a small 10-minute break, and let's be back. It's 11:20 now, so let's be back by 11:30, and we shall continue with our discussion. Welcome back, everyone. Let's move on to our next topic, and this next topic is nuclear fusion. Now, what we understood with nuclear fission is that nucleus breaks into two parts, and while breaking, it releases a lot of energy, and that's the energy that we want to use. In case of nuclear fusion, again, what is the meaning of the word fusion? What do we mean by fusion? To combine, to join, to merge, correct? So, right, so this is what we mean by nuclear fusion. So this is precisely what happens in case of nuclear fusion, that you have two hydrogen nuclei and they join together, and while joining they release a lot of energy. What we had discussed, let's say something like mass defect, that while they combine together they release a lot of energy. So this is what will happen in case of nuclear fusion, that two hydrogen nuclei will come together, and while coming together they will release a lot of energy. Now, if you look at what exactly happens in case of nuclear fusion, so occurs when two lightweight nuclear fuels are combined and they form nucleus of a heavier element while releasing a lot of energy. Now, if you see this, these are the reactions that happen inside the sun. This is what takes place inside the sun. Now, as you can see, inside the sun, what happens is that first two hydrogen nuclei will come together, they will form deuterium, and from deuterium, we see that this deuterium will combine with more of hydrogen and they will form helium 3. And this helium 3 is unstable. This helium 3 is unstable, and this helium 3, that's why it combines with more of itself to finally form helium 4, which is stable form of helium. So what is happening in this reaction is that hydrogen is converting into helium. In this entire reaction chain that you have, hydrogen is converting into helium while releasing a lot of energy. While releasing a lot of energy, and this is huge amount of energy. And that's why between fission and fusion, the amount of energy that fusion releases is incomparable to the amount of energy that fission releases, because here the amount of energy will be enormously high. Just imagine the sun is able to light up this entire earth and the entire inner solar system, at least because of nuclear fusion. So that's the strength that nuclear fusion has. So overall energy that nuclear fusion could produce is way more than what nuclear fission can produce, and that's when nuclear fusion becomes very crucial in that sense. So in case of nuclear fusion, that's why what we see is that for nuclear fusion to occur, it is necessary it is necessary to bring two nuclei so close that nuclear forces between them become active and make them stick together. So that is basically what we see with nuclear fusion. Now, overall, when it comes to nuclear fusion, just understand this, that in case of nuclear fusion, uh, we need certain conditions for this fusion to occur. For these particles to come very close to one another, we need to create these conditions under which they can come together, and then only it is possible for them to undergo nuclear fusion. And these conditions can be very extreme conditions. For example, extremely high temperature. Extremely high temperature, extremely high pressure, and very strong magnetic field. So if you have these conditions for nuclear fusion, So if you are able to attain these conditions, then there is a chance that nuclear fusion can be made possible. Otherwise, under normal circumstances, nuclear fusion will never be possible. So that's why getting to these conditions itself is not that easy. We have to artificially create these conditions under which nuclear fusion can be made possible. So there are two major approaches that we use here. There are two approaches that we use so that we can make these conditions possible under which nuclear fusion can happen. So these two approaches, one is called as magnetic confinement and the second one is called as inertial confinement. All right. So magnetic confinement and inertial confinement. Now, in case of magnetic confinement, what we do is that we make use of very strong magnetic fields. We make the use of very strong magnetic fields, and only with the help of these strong magnetic fields, we are able to uh, get to a situation where magnetic confinement fusion can be made possible. And this is precisely what happens inside the sun, that there is a very strong magnetic field that the sun is surrounded with, and this strong magnetic field helps the sun get those conditions under which nuclear fusion can be made possible. Now artificially also we can do this, and we have done it in a certain in certain experimental reactors. So what we do is that we create a toroidal shaped magnetic field. Toroidal shaped. Do you know what is toroidal shaped? We have to create toroidal shaped magnetic field, and only under those conditions then we can confine the required particles which can undergo fusion. Yes, Gia, you are correct. Like a donut. So this is the toroidal shape. So you have the magnetic field that is in this toroidal shape. This is what a toroidal shape looks like. This is what toroidal shape looks like. So this is how we have the magnetic field, something like this, that we have a toroidal shaped magnetic field, and in the middle you would be trying to confine the plasma so that nuclear fusion can be made possible. So this is how we make the use of magnetic field to make the use of nuclear fusion, to make nuclear fusion possible. So it is something that naturally occurs inside the sun, and it is something that we want to create artificially if we want nuclear fusion to take place. And there are certain experimental reactors where we have been trying to get these conditions which can help us in getting nuclear, or help us make nuclear fusion possible. So now when it comes to nuclear fusion, also understand that there is another way in which nuclear fusion can be made possible, and with the help of this is with the help of inertial confinement. Now inertial confinement is where we use powerful lasers. We make the use of powerful lasers, and with the help of these lasers we try to confine the particles together. So basically we'll be trying to force the particles with the help of powerful lasers. So we will make sure that these lasers, which have very strong intensity, they will be pushing the nuclei together towards each other, and ultimately that is something that can lead to nuclear fusion. So overall this is what we want. All right, this is what we want in case of the other way in which it can be made possible. So this is called as inertial confinement. Now inertial confinement has been in the news. This is something that we have seen in the news last 2 years, first in December 2022 and then in August 2023. Now there was a breakthrough. December 2022, the scientists talked about a breakthrough in case of nuclear fusion. And after this breakthrough, they said that now nuclear fusion is just 20 years away. Some of the statements that were released was saying that now nuclear fusion is just 20 years away. Unfortunately, this is something that we have been saying for a very long time. That even you go back to the statements released by many scientists back in 1980s, there also they were saying that nuclear fusion is just 20 years away. Unfortunately, that 20 years has not become 19 yet. But you have to also understand that this is one of the most difficult and complex scientific concepts that scientists have been working on, very difficult to achieve. So it's no joke that they are not able to get to the required conditions yet. But meme makers will remain meme makers and they'll keep making memes. So anyway, so when we talk about breakthrough, understand what this breakthrough is. Until now, it's not that experimentally we haven't made nuclear fusion possible. We have made it possible. But the amount of energy we are spending in making that energy possible is huge. The amount of energy that we are using is more than the amount of energy that we are getting. It's like using 100 joules of energy to get 50 joules of energy. And that's not ideal, of course. You would want more energy there. Then only you can make it commercially viable. If you are exhausting more energy in producing less energy, then in that case, it doesn't make sense. Now, for the first time in December 2022, the scientists were able to produce more energy from fusion. They were able to produce more energy than from fusion than amount of energy used in operation. In producing that energy, they use less energy and produce more energy. That's why we talked about this fusion breakthrough, and this is something that they also repeated uh, in August 2023. So that's why we saw that this is how this has been in the news. And it's not that they produce a huge amount of extra energy. They were able to release 3.15 megajoules of energy from 2.05 megajoules of input, which was enough to boil few kettles of water. That's it. So that much extra energy they were able to produce, but at least extra energy for the first time they were able to generate. Until now, we haven't been able to do that experimentally. Even if we have succeeded, we haven't produced extra energy, and that is where the problem lies, that we have to generate more energy than we are spending, and then only it becomes commercially viable. And this is where we haven't been able to reach with the other set of magnetic confinement. So then in that context, there is this international thermonuclear experimental reactor, which is basically where we want to use magnetic confinement for nuclear fusion. Magnetic confinement for nuclear fusion. So this is an experimental reactor which is right now under construction in France. And only by 2035, we believe that it will be operational. This is going to be the biggest nuclear fusion plant of the world. Apart from, so here, when it comes to international thermonuclear experimental reactor, it is a large scale scientific experiment, aims to demonstrate that it is possible to produce commercial energy from fusion. That using fusion, using magnetic confinement fusion, we are trying to produce electricity or produce energy out of this reactor. Now here, this reactor, we are looking towards 500 megawatt of fusion energy to be produced from here on. Initially, this project was started by the Soviet Union, USA, European Union, and Japan, and later India, China, and South Korea. They also joined this new experimental reactor. So, in total, you have 7 countries or unions which are a part of this experimental reactor. So, this is where we are with regards to ITER. But under construction, it will take some time before it can start um, going through with its operation, and then we'll understand whether or not it is producing enough energy that we can use it commercially. Apart from that, one thing else that has been in the news is Japan's JT60SA reactor, which is basically testing the technology to be used in ITER. So now this, right now, for now, this is the world's largest fusion reactor, and this was for the first time fired up on 31st of October 2023. So even this is in works, and we see that this also uh, might become useful for us in the coming days. So overall, that's why we have been trying all the ways possible to make nuclear fusion uh, work. Now, to make nuclear fusion work is a big project that the world has right now. Because if we are able to understand how to use nuclear fusion, if we are actually able to understand how to use it and we start using it, then all the energy problems that the world has right now might end. Because fusion will be able to produce huge amount of energy with very small amount of fuel, a very small amount of hydrogen, that is. So that's why the amount of energy that you'll be getting then will be incomparable to any other source of energy. So that's why we are talking about this uh, with regards to in future of energy. So understand what is the advantage, what are the advantages that nuclear fusion has, and why we are talking about nuclear fusion so much. Why are we so much concerned about nuclear fusion? First, abundant amount of energy, right? Because as we discussed that with very less amount of hydrogen we'll be able to produce huge amount of energy. So that's the first advantage that it has. It will be able to give us more energy than any other source that we know of. And then it will be sustainable, because hydrogen is used, you have enormous amounts of hydrogen available, and then from there on we can produce a lot of energy sustainably for a very long time. So that's why sustainability is the other factor. No carbon dioxide, of course. This in this entire reaction there is no carbon, so there is no carbon dioxide, so no emissions, so very clean source of energy. So that's why it makes it a clean source of energy. No long lived radioactive waste. Now this is a problem with nuclear fission, because in case of nuclear fission it produces a lot of radioactive waste that can last for very long, that can remain in the environment for very long. And that is the reason why we are looking at no long lived radioactive waste being one of the advantages that nuclear fusion has. So long lived radioactive waste is an issue with nuclear fission. This is an issue with nuclear fission because nuclear fission produces long lived radioactive waste. Now, in total, so in terms of, let's say, uranium, or as a byproduct plutonium, they can remain in the environment for a very long time. So that's why we talk about long lived radioactive waste being one of the issues with nuclear fission. In case of nuclear fusion, the waste is tritium water. Waste in fusion is tritium water, which converts to normal water quickly. So that's why we are not worried about tritium water, because tritium water within seconds would have just changed to, or would have converted to normal water. Whereas in case of nuclear fission, we have long lived radioactive waste. For example, plutonium can remain in the atmosphere, remain in the environment for thousands of years. Half life of plutonium is almost 20,000 years, meaning that in 20,000 years it reduces to half of its original mass. 20,000 years. Whereas in case of tritium water it is just some seconds. So that's why no long lived radioactive waste is another advantage with nuclear fusion. Then limited risk of proliferation. Can you tell me what is proliferation? What is the meaning of proliferation? Multiplication, spread, correct. Rapid increase, correct. So proliferation basically, that's why, is associated with weaponization. That's why this is associated with weaponization of nuclear uh, fuel. So proliferation is possible in nuclear fission. As we discussed, that the same chain reaction can be used for producing electricity, and the same chain reaction can also be used for making a nuclear bomb. So that's why the same reaction proliferation is possible. Whereas in case of nuclear fusion, you cannot use the same process for creating any kind of weapon. For creating weapon, even if you have heard of hydrogen bomb, then hydrogen bomb is not based on this particular procedure, on this concept. It has a very different procedure altogether. So that's why the same method cannot be directly used, and that's why there is a very limited risk of proliferation in case of nuclear fusion, whereas in case of nuclear fission we know that it is readily possible. Then no risk of meltdown, that is nuclear accidents. We again know about nuclear fission, that how there is a possibility that leakages can happen. Some of the material, some of the particles can escape out of the reactor, and they can lead to nuclear accidents. So, and we have seen these cases of nuclear accidents in the past, whether in Japan, whether in USSR, whether in the US. We have seen all these cases. So that's why there are chances of meltdown in nuclear fission, but it's not possible in nuclear fusion. And then finally the cost. Once we are able to use it, once we are able to commercially use nuclear fusion, it can also potentially bring down the cost of nuclear fusion or cost of electricity altogether. So energy cost will decrease once we start understanding how to use nuclear fusion. So that's the reason why nuclear fusion is such a preferred option, although until now we do not see a lot of attention being given to it. That uh, the focus entirely has been on nuclear energy, or at up to an extent nuclear fission energy, but fusion is something that is not really discussed a lot. And although if you look at the situation, if you look at the kinds of advantages that it gives, probably there is no other source that is better than nuclear fusion. So that's why nuclear fusion has to be seen as the future. And as soon as we are able to crack it, whenever those 20 years finally happen, this will be when you will be able to use this energy to your advantage. Please read this question. This was asked in your 2016 prelims paper. I'm launching the poll for you. It's a very easy question. I hope that you all answer it correctly. Hmm. So 73% of you have given the correct answer. Some of you have missed it. Let me discuss this first. India is an important member of the International Thermonuclear Experimental Reactor. If this experiment succeeds, what is the immediate advantage for India? International Thermonuclear Experimental Reactor. What did we discuss? That this is where magnetic confinement fusion will be used. Correct? This is related to magnetic confinement fusion. First option says it can use thorium in place of uranium for power generation. Now, thorium and uranium are related to what? They are related to fission. So that's why it can't be the answer. It can attain a global role in satellite navigation. It has nothing to do with satellite navigation. It can drastically improve the efficiency of fission reactors. It is not about fission, it is about fusion. This is wrong. So that's the correct answer will be D. It can build fusion reactors for power generation. That is what we are trying to crack, that we should be able to commercially make it viable to use nuclear fusion. And that is exactly what will happen if ITER succeeds. Now coming to nuclear technology, starting with nuclear reactors. But before that, if you have any questions, any question from whatever we have discussed in nuclear fusion? Fusion of nucleus or neutrons happen? Nucleus. The nucleus will fuse together. They will join, combine together. Using variable devices causing absorption of radioactive material more than the standard amount. Recently in the newspaper, I asked you that if you have the link to this news article, if you can send me this link, I would be better able to help you. Tritium becomes next what? Tritium, not tritium, but tritium water. Tritium water becomes normal water. Any disadvantage of nuclear fission? Nuclear fission, yes. I mean, nuclear accidents are possible. Radioactive waste is a big problem. Nuclear pollution is a big problem. So there are many. Fifth advantage of fusion. Fifth advantage, limited risk of proliferation. Proliferation means spreading, meaning when you're doing more enrichment. So we discussed that when you do more enrichment, you can create nuclear weapon, you can create an atom bomb out of the same process. So that is what we mean by proliferation. So chances of proliferation in nuclear fission is high. In case of nuclear fusion is very low. What about electron in an atom? Electron does not participate in any one of these nuclear reactions, because it's all related to the nucleus. Electrons are not related to any one of these things. Please just explain about inertial confinement fusion. So in inertial confinement fusion, what we are saying is that you try to use lasers, and with the help of lasers we try to bring these two nuclei together. We want to bring these two nuclei very close to each other so that they can fuse together, they can join together. Because just understand this, that when we were talking about uranium or plutonium or let's say thorium that we'll discuss, so these are very bulky and these are unstable. But hydrogen is not unstable. So it's not that it can naturally just undergo reactions. You'll have to make it undergo reaction. And that's where confinement approaches have to be used. And in inertial confinement, we make the use of lasers. We use strong lasers to make them stick together, to make the two nuclei stick together. Email ID. My email ID is rashesh.kumar at byju's.com. RASHESH dot Kumar at byju's.com. Nuclear energy is renewable or not? As we discussed yesterday, that we can neither call it completely renewable nor we can completely call it as non-renewable. How nuclear fission neutron produces their three neutrons? So I just discussed this, that I mean in that entire reaction, when it is splitting, while splitting there are three extra neutrons which are coming out. It is splitting into two nuclei plus three extra neutrons are emitted. So that's basically something that is happening, and it's a part of the reaction chain that you have there, that the neutrons will come out. Why not using another element for nuclear fusion? It becomes extremely difficult. The kind of energy that we can release is only possible with hydrogen. With others, fusion becomes very, very difficult because of their nuclear size. As the nuclear size increases, with increasing nuclear size, it becomes impossible for fusion to occur. Right then. Now, let's understand nuclear reactors. Now, nuclear reactors is where you would use nuclear fission to generate electricity. That is what the role or the requirement of nuclear reactor is. Now, in a reactor, we have different types. There are different parts of the reactor. First, you have the core. Now, core of a reactor is where all the nuclear reactions occur. The uranium, for example, the uranium 235 will be present at the core, and this is where the nuclear reactions would occur. Apart from the core, you have the control rods. Now, control rods are required to control the number of neutrons. As we discussed, that the number of neutrons that you have, the neutrons will lead to a chain reaction. To control that chain reaction, you need to ensure that the number of neutrons does not go uncontrolled beyond a certain limit. So if you have extra neutrons more than what's required, then control rods are used. These are metal rods which will be inserted inside the core when there are extra neutrons, and they would absorb extra neutrons, and then they will be pulled out of the core. So this is how control rods are used in a nuclear reactor. So control rods, that's why remember that these are metal rods to control the number of uh, these particles. Then after that, as you can see, you have a reflector, which is like, you can say, a wall that you are creating, a thick wall that you are creating, so that nothing should escape out of the core, to ensure that all the particles that we have, all the neutrons that we have, the neutrons do not go out, the gamma radiations, they do not go out. To control them inside the core, we use a very thick steel walls or concrete walls, and that is what the reflector is. And then after that, you have a coolant. Now, in case of a coolant will basically carry the energy from the core to the turbine. So coolant can be, for example, water or steam. That water comes in contact with the core has already produced a lot of heat energy, so water converts into steam. This steam will be carried outside. So that's why coolant basically is a material that will conduct the heat from the reactor to the uh, turbine. Then apart from that, another part that we have inside the core is a moderator. We have a moderator inside the core. Now this moderator controls the speed of the neutrons. For effective nuclear reaction, what we need is that this core, or the neutrons that we have at the core, they should not be traveling at a very fast speed. So to control the speed of the neutrons, we use moderators. So that's why remember that when it comes to control rods, they control the number of neutrons, and the moderators, they control the speed of neutrons. So that is the role of moderators and control rods. All right. And coolant basically will carry the heat energy from the reactor, that is the core, to the turbine. This is the role of a coolant. So that's why these become very important parts of any given reactor, any given nuclear reactor. So that's why the entire setup will be inside the new reactor vessel. So reactor vessel holds all the other parts of the nuclear reactor. Then you have the core. Core is where you have the nuclear fuel, and that's why it's a part of the reactor where fission occurs. Then you have the control rods. These are metal rods having elements such as boron or cadmium, and they would absorb free neutrons, helping controlling the chain reaction. Then we have the moderators, and moderators can be water, carbon, etc. They would slow down the neutrons which pass through it. So that is basically what we see with moderators. Then we have the coolant, and coolant is something like water or carbon dioxide or liquid sodium sometimes, which conducts heat well and does not easily absorb free neutrons. Because if it absorbs free neutrons, what happens? You already have control rods for absorbing neutrons. If coolants also absorb neutrons, then number of neutrons will be lesser than what is required. So that's why we have to ensure both. One, that uh, uh, coolant should be able to conduct a lot of heat, and second, it should not absorb anything out of it. So these are the parts of any given nuclear reactor. Now, in all these nuclear reactors, what we see is that there are various different types of nuclear reactors. There are various different designs of nuclear reactors which are used all across the world. Now, we are not really concerned about all the different types of nuclear reactors, but the ones that are found in India, the ones that we have been using in India, they are the ones that we should know of. So, what are these reactors? The first and the most popular and the most commonly used nuclear reactor is pressurized heavy water reactor. Pressurized heavy water reactor. Now, in case of pressurized heavy water reactors, we are using enriched uranium. We are using enriched uranium as fuel. We are using heavy water as moderator and coolant. So, both moderator and coolant is heavy water. Now, understand a few things which regards to what exactly this pressurized heavy water reactor is. So, obviously, we know that through cooling water or through the coolant, the energy that is generated in the core will go to the heat exchanger where you have the turbine present. So, this is where we see that the things will work. Now, understand one important thing with regards to how a pressurized heavy water reactor works. So, there are two things that you have to understand. Why are we using pressurized reactor? All right, why pressurized? And second, why are we using heavy water? Why pressurized and why heavy water? Now, something that we discussed yesterday with geothermal energy, if you remember, we discussed that at high pressure, water being in its liquid state can absorb more heat, right? Water being in its liquid state can absorb more heat even at high temperature. So even if you have a temperature of 150 degrees Celsius, water will still remain in its liquid state yet absorb a lot of heat. So heat absorption efficiency increases for water at high pressure even at high temperature. So this is why pressurized. All right, so why pressurized? Because at high pressure, water, without converting to steam, even above its boiling point, that is 100 degrees Celsius, can absorb heat more efficiently. Alright, so this is what happen, that when you have high pressure, even if you have a temperature of 150 degrees Celsius, water will remain liquid and it will be able to absorb a lot of heat. That's why pressurized. All right, that's why pressurized. That's why we see that. Uh, Sorry, this has to be without converting to steam, even above its boiling point, can absorb heat with more efficiently. So that's why pressurized. and hence we maintain very high pressure. If you see here, we have these pressure tubes, and these pressure tubes will ensure that high pressure is maintained in this reactor. Now the second thing is heavy water. Why heavy water? Do you know what is heavy water? Do you know what is heavy water? Can you tell me what is heavy water? Yeah, heavy water is D2O. So D2O meaning what? That there is deuterium being used. We are using deuterium. So this is called as D2O. Heavy water is deuterium. Now, this is deuterium based water. Instead of using normal hydrogen for this water, we are using deuterium for water. Why? The reason is deuterium has one extra neutron. Because of that extra neutron, it wouldn't be able to absorb any extra neutron easily. With normal water, there is still chances that normal water would have absorbed extra neutron. But with heavy water, because it has an extra neutron, becomes extremely difficult for it to absorb any neutron. So this also helps us in improving the efficiency. Now, in that sense, then you will ask me, why not tritium water then? Tritium water has two neutrons, so the chances of it absorbing neutrons becomes impossible. Why not use tritium water then? We don't use tritium water because tritium water is radioactive. It is radioactive, it is very highly unstable, and it will very quickly just convert into another form of water. So that's why tritium water is not usable. All right, tritium water is not usable. Heavy water, that's why you can say, hits that sweet spot where it is neither absorbing and at the same time it is efficient. So why heavy water? Because heavy water has an extra neutron because of deuterium. Making chances of neutron absorption very low. All right, so that is why extra neutron. So extra neutron meaning that they will then not absorb neutrons from the reactor core. So that's why pressurized heavy water reactor. Now pressurized heavy water reactor is the most common reactor design, whether in India or across the world. This is the most common reactor design. If you take India for instance, India in total has 21 reactors that we are functioning with. Out of 21 reactors, 18 reactors are pressurized heavy water reactors. And then there are two more reactors which are called as boiling water reactors, and then there is one reactor which is fast breeder reactor. So overall, that's why this is the most common reactor design. This is the most common reactor design, not only in India but across the world. So what we see in this reactor design is that you have all these fuel elements which are made of uranium 235, or fuel rods as we call them many a times. Now they will be there in the reactor core. The nuclear reactions will occur there. You have control rods which will help ensure that if there are extra neutrons, that can be taken away from the reactor. Now then the heavy water that we have is kept at high pressure, right? It is kept at high pressure, so we have steam generator that will convert this heavy water into steam, and this steam then will be carried to the turbine. The steam will be carried to the turbine, and from the turbine it goes to a condenser. it goes to a condenser, and from the condenser it comes back. So basically you have steam before that it goes to a turbine. You have steam here, and then it, after condenser, it has converted to water. Then after this you have a pump, and with the help of the pump you will be sending water back into the reactor. So in this manner, steam to water again will be sent back, converts into steam with the help of steam generator, and this cycle continues in the pressurized heavy water reactor. So this is how pressurized heavy water reactors work. The second reactor that India has is boiling water reactor. Now there are two boiling water reactors that India has, and these were the first two reactors that India started working with. So initial first two reactors of India were boiling water reactors, and then after that we switched to pressurized heavy water reactors later. But India's first two reactors were boiling water reactors. Now in case of boiling water reactors, what we see is that we make the use of enriched uranium, right? We make the use of enriched uranium as the fuel, and moderator and coolant is normal water. That's why water and not heavy water. Now, overall, when it comes to the working is a bit simpler because water will be fed to this reactor. You have the fuel elements and the control rods here. Water is fed to this, and then this converts directly into steam because you are not maintaining high pressure. So water, as soon as it gets in touch with the heat, water will convert into steam, and this steam again goes back to the turbine. From the turbine it goes to the condenser, and from the condenser it goes to the pump, and through the pump it is back in the reactor. So in this manner you have all this entire mechanism which works as boiling water reactors. Now, boiling water reactors are not as efficient as pressurized heavy water reactors are. So that's why after the first two boiling water reactors, we did not build any new boiling water reactors. So that's why these are the only two boiling water reactors that India has. Now, one very important reactor is fast breeder reactor. Now, again, try to first decode the words fast breeder reactor. Now, what do we mean by a fast breeder reactor? First thing, when it comes to a fast reactor, the term fast is mainly because they don't use moderator. Now, what is the role of moderator? We discussed that moderators will slow down the fast moving neutrons. In this kind of a reactor, we do not need to slow them down. So when we do not need to slow them down, we don't need the moderator. So we don't use the moderator in this case. So this is a reactor that does not use moderators. All right, it does not use moderators, and that's why these are fast reactors. That's why the term fast is being used. Then apart from that, the second term is breeder. Now, breeder is because there is kind of breeder is coming from the term breeding, meaning reproduction, and this is mainly because the amount of byproducts that we produce here is more than the amount of reactors or reactants that you had used. So the amount of fuel that you had used is less than the amount of byproduct that you are producing out of this reactor. So that's why produces more amount of fissile material than it consumes in operation, meaning generates more new fuel than the fuel that it spends. Now this is very special about fast breeder reactors, that let's say you are using 100 grams of plutonium and you are getting 150 grams of plutonium, which can be used again in this reactor, and you can keep using it for a very long time. And this is precisely where I had said that uh, when we start using fast breeder reactors, nuclear energy starts becoming closer to being a renewable source of energy, because you can use fast breeder reactors for a very long time without spending that energy. So because the byproduct is same as what you had used, so you can keep using it over and over again. So that's why fast breeder reactor becomes very crucial. And as far as the fast breeder reactors go, there is a fast breeder reactor called as two fast breeder reactors, one which is called as fast breeder test reactor. Fast breeder test reactor. Now fast breeder test reactor basically has been in operational for over 30 years now. It has been operational for about 30 years. And then there is another one that is under construction. This is prototype fast breeder reactor, right? Prototype fast breeder reactor. Now this is under construction. Right, this is under construction. So one is fast breeder test reactor, which has been operational in India for almost 30 years now, and then there is the fast prototype fast breeder reactor, which is under construction. Now it has been under construction for a very long time. Back in 2012, during the time of the previous UPA government, the government was asked uh, about the situation with prototype fast breeder reactor and when we should expect it to be operational. And back in 2012 they had said that it should be ready in the next 1.5 years. We are expecting that in 1.5 years it should be ready. 10 years later, then this government was also asked about the same, that can you tell me when it is going to be operational? And then the government said maybe in the next 1.5 years. So 10 years later the government's changed, the answer did not, that it is still believed to be under construction and it is still 1.5 years to 2 years away. Now some of the unofficial statements have been regarding the fact that the construction has been probably completed, but the problem is with the safety of the reactors, that the scientists still do not feel that it is very safe, and that's why they do not want it to make operational yet, that they are working on the security parameters of this reactor, and they are trying to ensure that it is a very safe reactor before we can make it operational. And that is believed to be the reason why it is still not in operation, and why we are still looking for it to become operation in the coming years. So this is fast breeder reactor. Now overall, when it comes to India, there is this. So this is what a fast breeder reactor looks like. I mean, you do not need to go into the complexity of the diagrams, and you don't even have to draw these diagrams in your examination. The basic thing, if you see, is the same, that you have the same core, you have the same control rods, you have this time, you have the steam generator, then there is the pump, there is the turbine. So there are all these things which are the same. You have the condenser, just as we saw in the previous uh, case as well. So all these things remain the same, just that here the coolant that we are using is different. All right, the coolant that we are using is different. The coolant here is liquid sodium. Coolant here is liquid sodium, and it's not water as was the case with the other two. So liquid sodium is being used as the coolant. Now, based on all this, we have India's nuclear program. Now understand what India's nuclear program is, and also a brief history into India's nuclear program, that what do we mean by India's nuclear program. So in case of India, we know that we have pressurized heavy water reactors, and now we have the boiling water reactors, and we also have the fast breeder reactors. Now, essentially, this nuclear program is a three-staged program. There are three stages of this program. In the first stage, we are using pressurized heavy water reactors. In the second stage, we are using fast breeder reactors, and in the third stage, we are using something called as advanced heavy water reactors. Now, why these three stages? Understand the whole idea behind this entire program that India uh, wants to use. So if you see, the first stage comprises of pressurized heavy water reactors, and then the second stage for the fast breeder reactors, and the third stage based on thorium uranium 233 cycle. Now understand this, that what are we talking about, and what are these three stages of India's nuclear program. Now, in general, what we understand is that uranium is the primary fuel when it comes to nuclear fission, right? Uranium is the primary fuel. In India's nuclear program and elsewhere in the world also, uranium becomes crucial. Now, in case of India, we have vast reserves of thorium. We have vast reserves of thorium. Now, thorium directly cannot be used as a fuel, not like what happens with uranium, but we can make thorium fissile. We can make thorium something that can undergo fission. So we can make thorium fissile, and that's why we wanted to have this entire program so that we can start using thorium instead of uranium, because India has vast thorium reserves and we have very limited uranium reserves. Thorium reserves in India is among the top 5 countries in the world, if not top 2. If you look at some data, it will say India is the next country after Australia when it comes to thorium reserves. And in some cases, you'll see that India will be listed among the top 5 countries in the world with regards to con- thorium reserves. So precisely this is what we want, that we want to use thorium instead of uranium in our nuclear reactors. So why the program? To use thorium instead of uranium, thorium instead of uranium in the nuclear reactors. To use thorium instead of uranium instead in the nuclear reactors. So this is what we want. And this entire 3 stages that we developed was only to get to the part where we can start using thorium instead of uranium. And this program was brought forward by, it was proposed by Dr. Homi Jahangir Bhabha. Now, Dr. Homi Jahangir Bhabha has been one of the most important scientists of the post-independence India. Because just after independence, he, along with some of the other scientists like, let's say, Vikram Sarabhai or Satish Dhawan and all these scientists, they became the most crucial scientists who took up the job of, you can say, India's scientific development. And Dr. Bhabha was very aggressive with regards to India's nuclear program. He had suggested that if India has to grow, if we are looking towards India's energy future, then coal is not the answer, nuclear energy is the answer. And he used to propose nuclear energy just after independence also. Although it was not easy to propose nuclear energy back then, because in 1947, when we got our independence, 1947 was just 2 years after what we had seen as an atom bomb in Japan. What happened in Hiroshima and Nagasaki, it happened in 1945. So just 2 years after that, when we get our independence, it was very difficult for anyone to propose to use nuclear energy for peaceful purposes for electricity, because the entire world was afraid of it. So that's when nobody wanted to go and adopt nuclear technology at all, because it would create a lot of international controversy. So even when, but he kept on pushing for it, and ultimately he devised this 3 stages of the program so that ultimately we can start using thorium instead of uranium in India. So, and that's why he has been one of the most prolific scientists of the time. The atomic program that India developed, it is, you can say, in a manner, it has been all thanks to him and his efforts after the independence. Unfortunately, he did not live for very long. He died in a helicopter crash, and it was 1967, I think, when he lost his life. So unfortunately, he lost his life to an accident. Otherwise, the way he was moving, he could have done a lot more for India. And it is also said that the accident that happened, it may not have been a natural accident, but rather something that was uh, where US probably would have been behind causing this accident. The Central Intelligence Agency, or the CIA of the US, probably was behind causing this accident, because they knew how fast India was moving, and they did not want a new power to emerge out of a country like India. And we do not know what happened and what didn't, but one of the ways, it always has been a theory that it is something that was programmed by the CIA. So The India's nuclear program is where we are talking about the three stages of nuclear program, so that ultimately we can start using thorium instead of uranium. Now, if you look at the nuclear reaction or the three stages, the first stage is where you have the conventional nuclear reactors, where you have pressurized heavy water reactors. You have pressurized heavy water reactors. So pressurized heavy water reactors will be used. Natural uranium or uranium 235 is used there. We get electricity from here and we produce plutonium. We get plutonium out of this. Now, this has to be operational for almost 30 years for us to get enough plutonium for the second stage. All right. Now, also remember that plutonium is not natural. Like, let's say, uranium. In case of uranium, we know that uranium is naturally occurring. So, we can mine for uranium and we can use it in our reactors. That's not the case with plutonium. Plutonium is artificially produced out of these kind of reactions. So, whenever this reaction will occur, this is when we'll see that it will lead to the production of plutonium. So unless we have enough of plutonium produced out of this reactor, until then we cannot start with the operations of the second stage. So in the second stage, we have the fast breeder reactors where plutonium is being used and you are getting plutonium out also out of this reactor. Now this is where irradiation of thorium is done. Irradiation of thorium. Now understand the meaning of the term irradiation. We are saying that we carry out irradiation of thorium. Irradiation means that radiations are being passed through thorium. Passing radiations through thorium, that is thorium 232, to convert it to uranium 233. All right. So with the help of this irradiation of thorium, we are converting thorium into uranium 233. Now this also has to be operational for at least 30 years. These fast breeder reactors, they also have to be operational for 30 years so that we get enough of uranium 233 that can be used in the third stage. So third stage is where we have the thorium reactors, where we have something called as advanced heavy water reactor. Advanced heavy water reactors. So these advanced heavy water reactors will be used in the third stage. These are also breeder reactors. All right. These are also breeder reactors. Now, advanced heavy water reactor right now is under construction in India. So whenever the construction is completed, we might see that we would want to move to the third stage. So until now, we haven't been able to move to the third stage. We ultimately want to move there. So again, thorium irradiation will keep happening and it will keep converting into more of uranium 233. And with this, we have estimates that at least for the next 500 years, with 30 years of operations in stage 1 and stage 2, we will be able to have enough uranium 233 and thorium to keep running our power plants for the next 500 years. That's the importance of thorium. That's the importance of this entire India's nuclear program, because this is what will help us in getting to a stage where all this can become possible and we can become energy secure. So that's why India's nuclear program becomes very crucial from the perspective of where we are and where we want to be. Now, lastly, coming to the applications of nuclear technology. But before that, if you have any doubts with whatever we have discussed in all the nuclear reactors and India's nuclear program, any question if you have for me? Explain PHWR again. So, in case of pressurized heavy water reactors, what we are simply saying is that you are maintaining high pressure. By maintaining high pressure, water will remain in its liquid state and yet conduct all the heat required even at very high temperature. So that's why we maintain high pressure and we use heavy water here, so that heavy water is more efficient as a moderator and a coolant as compared to normal water. And here what we do is that the fuel elements is where the reactions will occur. The heat that is being generated will be taken to a heat steam generator where you generate steam. Steam is taken to the turbine, which will make the rotation of the turbines happen, and this is something that will lead to electricity generation. So that is what we do in pressurized heavy water reactors. Some doubt with second stage and third stage fuel elements. Can you elaborate on what doubt you have? I can help you with it. Which isotope is necessary in nuclear reactions? Uranium 235, 8, or 33? Every reactor has a different requirement. I mean, most of the reactors that we have in the world right now, they are using uh, they are using uranium 235, but we know that in certain cases we can actually make the use of uranium 233 also, and that's mainly the case of uh, the breeder reactors. That breeder reactors is where we are making the use of it. What is calandria? So see, calandria basically is used to insulate the pressure tubes, the high pressure tubes that we have. The insulation of that is done with the help of calandria, and this insulation will help in ensuring that the outer temperature does not affect the inner temperature of the core. So that's why calandria will be used in this particular reactor. What safety issue are facing by prototype fast breeder reactors? So safety, we do not know the details of what are the safety problems or issues that they are facing, but safety in case of nuclear reactors always mean that we are concerned about the number of neutrons and the reaction going uncontrolled. So that's where the safety concerns come from. Didn't understand how pressure of water can lead to creation of energy in. No, pressure of water does not create energy. Pressure, high pressure of water will only ensure that it does not convert into steam, and it remains in its liquid form even at high temperature. That even if you are at 150 degrees Celsius, it still remains liquid instead of changing into a gas. First prototype FBR is in ICR. Yes, it is, but they are. I mean, under construction. If I'm saying, it's not about the fact that construction is not completed, but rather that they still haven't been ready enough to launch it and start using it. They did use it. I mean, they did reach criticality on it, but at the same time, they found certain problems with the leakages and the problems associated with uh, the safety features, and hence they still haven't gone ahead with starting to use it. I have some confusion in fast breeder reactors. Plutonium produced from first stage is the fuel. Yes, it is. And thorium is added as a fuel. No, thorium is not added as a fuel, but radiations are added on thorium. So what we do is basically we add thorium here and irradiation of thorium happens, meaning radiations are passed through thorium so that thorium can convert into uranium 233. Nuclear reaction release heat which convert water into steam, which in turn rotate turbine to generate electricity. Yes, of course, this is perfectly what happens. You are correct here. Then what does it lead to if it doesn't create steam? It remains as water. It doesn't create steam. It remains as water. Can you repeat last sentence? 30 years production to 500 years. Basically, what we are saying is that through 30 years of operations in first stage and the second stage, the amount of uranium 233 that we get will be enough for us to keep using this third stage for the next 500 years. This is what I'm saying. Can uranium 233 undergo fusion? No, fusion cannot happen. Fusion will only happen in hydrogen. No other element will be able to undergo fusion. What is the outcome of pressurizing water? That water will be able to remain in its liquid state. Just remember this, I'm repeating for the fifth time. Water at high pressure, even if you are at high temperature, even if you are at 150 degrees Celsius, normally what happens? Normally, water would have converted into steam at 100 degrees Celsius. Water boils at 100 degrees Celsius, right? But when you have high pressure, when you apply high pressure, water does not boil at 100 degrees Celsius. Water still remains liquid even if you are at 120, 150 degrees Celsius. So it will be able to absorb all the heat and not convert into steam. Recently, Japan floating the nuclear waste water into sea. How the water is non-reactive? So the argument that they are giving is that they are only already treating the water before releasing it, and that's why there are no chances of any radioactivity increasing in the seawater. Okay, you were asking about whether 233 can undergo fission. Yes, from uranium 233, fission is possible, and that is what we will use in the thorium based advanced heavy water reactors. So it is possible. In fast breeder reactors using plutonium, are we generating thorium? No, we are not generating thorium. Thorium is being fed into the reactor from outside, and then radiations are passed through this thorium to convert it into uranium 233. Lunch break will take after the completion of this chapter, which will take like 20 odd more minutes, 20-25 minutes. After that, we'll take the lunch break. To get to uranium 233, we need thorium. Absolutely correct. Yes, we do. What happens to plutonium in stage 2? We will keep on generating more and more of plutonium so that we can use it in the future, and we can keep using the fast breeder reactors for as long as we can. There was a line in the PPT: irradiation of uranium 238 produces plutonium. What is its significance in the reaction? So when we have plutonium, I mean, what we do is that from plutonium, I mean, from uranium 233, with the help of passing radiations through uranium 238, we try to produce plutonium from there, and then that plutonium can also be used as a fuel. It can be used as a fuel in uh, uh, the second stage, that is the fast breeder reactors, or in general plutonium otherwise also can be used in other aspects and other ways also. All right, so let's move on to the last topic of this chapter, and this is about the application of nuclear technology. So first application is in agriculture. Now, until now we have been talking about only electricity, and obviously producing electricity is the most important application of nuclear technology. Nothing is more important than producing energy, generating energy out of it. But there are other applications where we make the use of radiations, especially we make the use of radioactivity in all these cases. So water use and soil management, in pest control, in ensuring animal health and productivity, in ensuring food safety, in all these cases we see that controlled radiations are used. Controlled radiations are used, and by doing that we can use, for example, let's say in soil management, we add we use radiation so that we can kill the growth of microorganisms, harmful microorganisms there. So that's why this is something that we do in case of soil management, and in water purification also, in water, from water also, to remove all the pests, etc. We can do that. Similarly in pest control, otherwise also, these radiations become helpful. Overall, many a times we see that even in ensuring food safety, we can pass them through radiations so that the decomposers or the microorganisms developing inside them, they can be taken care of. So all that can be done as a part of agricultural application. Similarly, we also have nitrogen 15, and nitrogen 15 is also called as nuclear fertilizer. It is called as nuclear fertilizer, and this nuclear fertilizer becomes helpful in us understanding and determining the optimum ratio of fertilizers to be used. That what's the optimum ratio of fertilizers can be understood with the help of nuclear fertilizers. So nuclear fertilizers, they help us optimize fertilizer amount to be used on a crop. Then, apart from that, in case of carbon dating is where we make the use of carbon 14. And with the help of carbon 14, we see that this is where we try to accurately date the historical artifacts. That anything that is up to 50,000 to 60,000 years old, we can find the age of all these elements and all these, let's say, fossils with the help of carbon 14. Now, what happens is, how we are able to use carbon 14 here is that carbon 14 to carbon 12 ratio in any organism that is alive is fixed. There is a fixed amount of carbon 12 to carbon 14. But when, let's say, any plant or an animal dies, carbon 14 will now become fixed. There is no extra addition of carbon 14, carbon 12 happening anymore. And carbon 14 being radioactive, it will keep on decreasing in its quantity, because it will keep on emitting some particles, it will keep on decreasing in its quantity. And this is where the concept of half life comes in. So half life basically is the time in which a radioactive element decreases to half of its original value, or how half of its original mass. All right. So time period in which a radioactive element decreases to half of its original mass is called as the half life. So for carbon 14 half life is 5700 years. For carbon 14, the half life is almost 5700 years. So in 5700 years, it would have decreased to half of its original mass. Now, in case of, that's why we try to determine how much of carbon 14 is still left, because carbon 14, how much it would have decreased, it can be calculated. So from that perspective, we are able to understand the age of any given article or any given fossil. Then after that, there are industrial applications as well. So in case of industrial applications, what we see is that they can be used in various different ways, like non-destructive testing, enhancing material quality, electrostatic control. Now in all these cases, what we observe here is that it's more about understanding and adding or strengthening of material. It is strengthening of material, that they can add strength to the material, and even we can enhance the material quality, and we can understand what the strength of the material is, and accordingly there are composite materials that can be made with the help of these radiations. So that's why we see that they can be useful here. Similarly, in case of oil and gas exploration, they can help us in determining where the location of any oil or natural gas is. So they can actually be useful in all these purposes also. Then they also have medical applications, and very well known when medical applications, where we can make the use of them in radiology. We can make their use in radiology. Now radiology basically is where we are making these radioisotopes and we are using them for treating certain diseases. For example, in case of cancer, in in killing the cancer cells, we make the use of radioactivity, we make the use of these radiations to kill the cells that have become cancerous. So that's why in radiology it becomes very very crucial, and that's why in medical application also we see their use. And then lastly, using nuclear technology for space exploration. Now, in case of space exploration, what we see is that we can make the use of something called as radioisotope thermoelectric generators, or RTGs. Now, this is something which ISRO now also has developed, and this is something that will help especially when we are taking deep space missions, the missions where we are going beyond, let's say, the inner solar system. We are going, let's say, towards Uranus or Neptune or Pluto, etc. Then solar energy is not useful. When we are near the earth, here the solar intensity is very strong, so that's why solar energy can be used very easily. But as you move out, this is where you cannot use solar energy anymore. So that's why these kind of uh, fuel can be useful, and this is where we want to make the use of isotope, that is plutonium 238. So with the help of plutonium 238, we can actually make it as very useful in nuclear fuel. So there are all these things that we have been doing. There are all these ways in which, in one way or the other, nuclear technology can be useful. Now what I've also done is, and this is something that I'll ask the team to share with you, I have a list of radioactive elements. I've made a list of important radioactive elements. That what is the radioactive element and what is the use of this radioactive element from prelims perspective, if not anything can be important. So just go through the list, only the ones that are important. I mean, there are a lot of radioactive elements and a lot of usage where they can be found to be useful, but I've only picked the ones which are the most important, and that's there in that list. So please go through that as a fact for your prelims examination, because sometimes questions can be asked, let's say a match the column kind of a question can be asked from here. So that's why you have to be ready for these things. So just use that. It will also help in, especially maybe in the prelims examination. So this is about this chapter. We When we come back, let's say after the break, let's first start with the mains PYQs in this chapter, that is energy, and then after that we'll move on to our next chapter, that is space technology. So we'll start with space technology next. There are 4 questions that have come from here, so we'll discuss about these 4 questions, and then we'll come back in the next class after the lunch break. So time almost is 1 o'clock. So let's be back by 2, and then let's start discussing our next chapter. All right.